Hello and welcome to this video on trigonometric substitutions. We're going to use a trigonometric substitution to find the integral from 1 to root of 5 of the square root of x squared minus 1 with respect to x. The trigonometric identity we're going to use to introduce a substitution is the following one. So notice that we have tangent squared of theta plus 1 equals secant squared of theta. So that secant squared of theta, take away 1, is equal to tangent squared of theta. Then when we take the root of the left-hand side, we find secant squared of theta minus 1 under the root equals the root of tangent squared of theta. And if we're thinking of tangent that is not negative, then this gives secant squared of theta minus 1 under the root equals tangent of theta. That's for theta between certain values. And the values we have here for x between 1 and root of 5 will be such that the tangent will become like this when we make x equals secant of theta. If we make x equals secant of theta, then the root of x squared minus 1 is the root of secant squared of theta minus 1, and that becomes tangent. And then dx turns out to be secant of theta times tangent of theta, because the derivative of secant is secant times tangent, and then times d theta. So then the integral we have from 1 to root of 5 of x squared minus 1 under the root with respect to x turns out to be a new integral of tangent of theta times secant of theta times tangent of theta d theta. And if x is equal to 1, then we're saying that secant of theta is equal to 1. So theta is equal to 0, or a multiple of 2 pi in general. But because we are going to focus on certain interval, we just take theta equals 0. While when x equals root of 5, we're saying that secant of theta is root of 5. So the cosine, which is the multiplicative inverse of theta, of secant of theta, is 1 over root of 5. Then theta is the inverse cosine of 1 over root of 5. Let me write that over here. Make some room. Take things by parts. There you go. So theta is the inverse cosine of 1 over root of 5. Okay, so we're working with the integral from 0 to the inverse cosine of 1 over root of 5 of tangent squared times secant of theta d theta. So we just turned an integral that involved a root into an integral of a trigonometric function. And to find the integral of this trigonometric function, we can use various tricks. This problem is going to get a little bit long, so let's go to a different page. Here, the integral from 0 to r cosine of 1 over root of 5 of tangent squared of theta times secant of theta d theta can actually be written as the integral from 0 to r cosine of 1 over root of 5 half. And when we replace tangent squared of theta by what it is, remember that tangent squared of theta plus 1 is secant squared of theta minus 1. So tangent squared of theta is 1 minus secant squared of theta. What we get is that we're taking the integral of secant of theta minus secant cubed of theta. with respect to theta. And we know the antiderivative of secant from the chart of antiderivatives. In the antiderivative of secant cubed, the most general antiderivative is something we found in a different video. I will leave a link in the description of this one. Here we have the antiderivative of secant, and that's going to give us actually we made a mistake here. This should be secant squared of theta minus 1. That makes more sense because tangent squared plus 1. Okay, sorry about that mistake. This should be secant cubed minus secant of theta. Okay, the antiderivative, the most general antiderivative of secant cubed is 1/2 of the ln of the absolute value of tangent of theta plus secant of theta, and then plus tangent theta times secant of theta. It's 1/2 times all that. And then we are subtracting and then we just leave the c out. We ignore the c because we're working with a definite integral. So theta is from 0, going from 0 to r cosine of 1/√5. And then we subtract the antiderivative of secant, which is the ln of the absolute value of tangent of theta plus secant of theta. And again, we're going with theta between 0 and r cosine of 1/√5. So here we have 1/2 of the ln of that addition plus 1/2 of tangent times secant minus 1 times the ln of the addition plus and then that's it. We can rearrange this expression in a way, we can rewrite this expression in a way that we see 1/2 of tangent of theta times the secant of theta, 1/2 of ln minus 1 times ln, that gives us minus 1/2 of ln of that addition. And theta varies between 0 and r cosine of 1/√5. And once we evaluate those functions at r cosine of 1/√5 and subtract the value of those functions at 0, what we get is the value √5 minus 1/2 of ln of 2 plus √5. Okay, so we have solved the problem by using a trigonometric substitution, and in the process we got to use trigonometric identities. That's usually the case when we're given an integral that involves a root. And in general, when we work with the root of x squared minus 1, when we see that type of expression, we like to use the substitution x equals secant of theta. That substitution is particularly helpful. And once we use that substitution, we get what we were given written in terms of trigonometric functions. So once we apply the trigonometric substitution, once we use it, then we get a trigonometric integral. And we know how to work with trigonometric integrals because that's something we have covered in the past. If you haven't seen those videos on how to work with trigonometric integrals, please watch them. There are some other videos here that in my channel that you can watch to see how trigonometric integrals work. Okay, thank you for watching. If you have questions, make a comment. I'll be happy to help. Bye-bye.